then there was an issue with your screen staying on, and that took another little deal, so it didn't run the battery dead. Okay, so here we are, first part, Industrial Fluid Power 1, Chapter 1. This is the Womack 3rd edition book, and hasn't changed in a while, but it's still good. So, I've added to this PowerPoint. This is not in your book. These PowerPoints are on the class share if you want to get them. But first we're going to have to come up with a defining a few things, and it's kind of physics terms, technical physics. Force. Alright? A force is a push or pull. You have the force of gravity acting on you now. Alright? Work. Work is a force applied through a distance. Okay? Jack up a car, force is being applied, but you don't do any work unless you're actually moving it up or down. Power. Power is work per time. If you do the same amount of work in a shorter time, it takes more power. So now I need a volunteer. Somebody that doesn't care to be on YouTube.
No, you don't want me.
I'm already on YouTube.
All right, come up here then.
I just come up here?
Yeah, yeah.
Cool.
Okay. I'm going to grab you by the shoulder. Don't let me move you. I'm applying a force to him, right? All right. Now I'm working because he moved.
Yeah.
Okay? Now if I shoved you really hard, I'd be applying more power than I did the first time. I'm not going to do that.
Okay. Okay. I was looking a little bit there.
Thank you. So now you understand the difference. All right? It's easy, but these are basic terms you need to understand because when we talk hydraulics, you know, there's a difference between moving something and applying a force to it. Okay? If you've had basic electricity, you should recognize kind of the Ohm's law or force triangle. Same principle applies. If we know two components of a hydraulic system, we can find the third by using this formula, as in force, area, and pressure. Force is in how many pounds per square inch is being applied. Area would be the area that the force is being applied to. And that gets a little confusing. And then PSI is pounds per square inch. Okay? So, like I said, now you guys can take these notes if you want to, or you can download the PowerPoint. I'm just saying. But however you want to do it. So, I like to use Wisconsin Online, and they have quite a few learning objects, and I want to show that to you real quickly. If you have any questions throughout this class, you can go to this website. And under Technical, Hydraulics and Pneumatics, there are little flash animations that will show us quite a bit. And they're a little bit easier to understand than me just lecturing. Okay. So that's kind of what I wanted to show you there. So, fluid power, basically the transmission of power from one place to the other using what? Fluid. There you go. So, first step in fluid power transmission is we got to have a pump, alright? Means of generating, moving the fluid. And it can be an air compressor or a hydraulic pump. Okay? Now, remember this is back to the very beginning. power, whether it's mechanical, electrical, whatever, okay, must always both consist of force and speed. Okay, that means it's got to be moving, just like voltage is potential, but once the current's flowing, we're drawing amps, so now we're transmitting watts and power, right? And just kind of a repeat, power is only being transmitted when the fluid's moving. All right, fluid doesn't move, we don't transmit power. So we got three methods for transmitting this power. Mechanical, shaft, gears, chains, your bicycle. That'd be a mechanical means of transferring power from your legs to the road and going on down the road. Electricity, lights, motors, drills, anything electric. And fluid power is the third way. All right? So, some of the advantages of fluid power are ease and accuracy of control, multiplication of force, okay? And you're wondering what that is. Well, how is it a single man can jack up a 2-ton truck using a hydraulic jack? How can they do that? They can't. It's the multiplication of force. A little bit of, just like a fulcrum and a lever, except we're using hydraulics. Okay, and we'll get into that later on, but that's what multiplication of force is. Basically, we use hydraulics just like a lever and a fulcrum. Constant force of torque. What that means is, using fluid power, if you need to have a clamp or a press or a mold operation using hydraulics, if you need to hold pressure on something, that's much better than, say, mechanical, which can, there's slippage in the gears. Electrical, there's slippage in the EM force of the motor, okay, unless you have some kind of positive traction planetary gearbox, there's going to be some kind of slippage on an electric motor, so you don't always apply that constant torque. Simplicity and safety. Why would we say safety on that? Because we just watched the Three-Fingered Joe video.
If you're using force, you're risking.
Huh?
The simplest way is the safest way sometimes?
Well, yeah. Think about this. If you're trying to transmit power using belts and pulleys and gears, how many pinch points do you have compared to running a hose all the way to where you need to use it? And you only got less pinch points, basically, because it's easier to move it. It's kind of contained in the pipe. Of course, the pipe can burst, but as far as pinch points are concerned, transmitting power through a pipe is much safer than a bunch of pulleys and sprockets. Yeah, well, there's not like a lot. Part of it goes back to maintenance. Typically, very rarely does a hydraulic system just blow a hose. Usually, there's a small leak or a bubbling of something to indicate that it's fixing to go, and it should be fixed before that happens. But yeah, they can just blow, just like a motor can explode or a drive can blow up capacitors and blow up. I mean, with anything made by man, eventually it's going to fail if it's a mechanical or electrical device. Just like the guy getting in the dump truck, and the guy said, you need to put the locking pins on because it would fall and crush him. You know, it doesn't matter what it is. Eventually it's going to fail. Okay? Eventually your car is going to break down. Your phone's going to quit working. It's just a matter of time. So, middle of page 10, there's some other advantages. I'd have to look. I don't remember what it said. But anyway, that's not too much. I think one of them is actually cleanliness. Let me pull up my notes here. Oh, vibration, space saving, relatively quiet operation. Instantly reversible motion. Now that's a big deal with hydraulics. You can't instantly reverse electric motors all that well. But you can with hydraulics. Now you may shear some keyways when you try to pull this off, but there are certain applications that are designed in hydraulics that you just about can't pull off with an electric motor because of the electromotive slip. Okay, so there is going to be that little gap. Give you an example of that. Like a palletizer that I don't know, you probably don't know what a palletizer is, but basically boxes come down and they put a layer of boxes and then the bottom falls out and it falls down on the pallet and then the plate goes back over and they put another layer of boxes like this. And so that up and down movement of the pallet to keep stacking boxes so we get a nice stack of boxes to send to Sam's Club is, if you have it with hydraulics, there's much more control over that than with an electric motor and a gearbox. Okay? Though I have seen them use both. Yeah. Alright. So, pretty simple. If we want to transmit force, we can do it this way. Right here we have the same size piston. If we put down 10 pounds of force on one side, then we get 10 pounds of force out on the other side. Make sense? Alright? It's confined fluid. Now, multiplication of force. This piston only has 10 pounds of force being delivered, but you notice the difference in size. Okay? It will not move as far. Just like your hydraulic jack, when you jack it up, you might have to jack it up 50 times to make it move 5 inches. But because of the surface area, we get the multiplication of force. So 10 pounds equals 100 pounds of force on the other end. Does that make sense? You're like, no, I get those looks. You got to believe me because you've seen a hydraulic jack. Alright? You have no choice. If you've seen a car jacked up, you have to believe me. Alright? If you believe in hydraulic jacks, you have to believe me. So here's a little acronym for a hydraulic system. Paul very rarely provides anything. Stands for piston, valve, what did R stand for? Reservoir, yeah. Pump, and actuator. Pipe, I'm sorry, and actuator. So, if you don't have this, you don't have a hydraulic system, is all that says. You with me so far? Of course, I can't ever remember that acronym, but basically, you need to know that a hydraulic system consists of pump, valve, reservoir, pipe, and actuator, because you got to have something to transmit the fluid to the actuator. Okay? This might make a little bit more sense to you. Here is a log splitter. How many have seen a log splitter work? You seen a log splitter? Same principle. Our pump is gasoline powered instead of electric. So, a little bit about compressed air. In here we generate compressed air with the compressor. We send it through a FRL, or filter regulator lubricator unit, because we have to clean the air. When we compress air, we also compress the moisture in it. Hence, we get water in compressed air. Okay? If it's 100% humidity outside and you compress it, that water has to go somewhere and it falls to the bottom of the storage vessel and the lines. We go through a 4-way directional valve, and here we go through some adjustable flow valves to an air cylinder. Notice that we only have one line, because in a compressed air system we will simply vent to atmosphere. We don't have to go back to our storage vessel. We just vent to atmosphere. That's all we have to do. Same principle in a hydraulic system. We have a relief valve and a pump. We have our reservoir, okay, and we have another little filter here, but we have an oil return line because we got to get that fluid back. You know, some of the new synthetic hydraulic oil, you might have a 50-gallon reservoir, and you're looking at synthetic oil. You're looking at about $500 or $600 worth of oil. So you want to get it back. You don't want to lose it. Now, this is comparing on page 14 the power level, or comparing an air system to a hydraulic system. Power level, well, hydraulic systems always will have the ability to transmit more power just by the nature of how they work. Air is compressible. Noise level, your book may say different, but there depends on how well maintained the system and how big. You know, they're both noisy. Now, cleanliness. Now, that was brought up earlier about who said the thing about building. Okay, maybe it is cleaner, but how nasty is the vent plugs on a pneumatic system when they overfill the oilers and turn them up too much, and you go over there and it looks like a oily dust blown all over the side of a piece of equipment from the vents. So I don't know. Is it cleaner? I don't know. Speed. Somebody turn to page 14. And what does it say about speed?
Lightweight systems operate faster with compressed air.
So they're saying compressed air is faster, generally speaking. I'm not sure that's all still exactly true anymore, because I've seen some pretty fast hydraulic systems. But if you're mostly, the whole point about the speed deal is you can get by with smaller piping, because compressed air, just by the nature, is going to move faster than oil, right? Because there's not as much resistance to the piping, because it's an air form instead of liquid. Okay?
It also says there is an exception when it is an accumulator system.
Yeah. Yeah. So it can, I don't know. Typically, though, if you want like a high-speed kickoff, you would do pneumatics. You wouldn't even think about hydraulics. Operating cost. All right, before looking at your book, what do you think costs more to operate, hydraulics or pneumatics?
I think hydraulics.
Pneumatics. Hydraulics is the most expensive to install. It costs more. But in the long run, it is the cheapest to run, because the biggest single waste in a plant, the most expensive thing to run, is air-operated equipment. And you're thinking, well, air's free. But the compressor's not. All right, and if it's a large system, because it's very inefficient to compress air and move it. In a large system, over years, we have get little air leaks. And so what do? Our compressor works harder. And when it can't do it anymore, we buy another compressor. Now we're running 2 compressors. Why do we have to run 2 compressors? Well, because we have tiny little air leaks everywhere. And I'll give you an example. I worked in a plant, and we were maxed out on our compressor. It was an older plant. And so instead of buying a $50,000 or $100,000 compressor, we went through the whole plant and fixed all the air leaks, and we were actually able to shut one compressor down, because all these little hisses, they add up. Okay? Rigidity, we talked about first cost. You know, I kind of argue with that. They're both pretty, you know, if you buy industrial pneumatics or hydraulics equipment, they're both pretty rigid. Okay. Blaise Pascal. All right. I have a little video on his discovery, so let's watch that. Let's watch his video. Didn't mean to put this in here. I might kind of put that right there.
Good day, this is Jim Pytel from Columbia Gorge Community College.
Oh, this isn't the one I wanted to watch. This one will put you to sleep. Anyway, I'll dig it up later. I'm not going to sit here and try to find it. I know I had it marked somewhere. Okay, let me introduce you, and this Womack series has quite a few books. Let me explain to you who this is. This is Ready Fluid. That's his name. And Ready Fluid is demonstrating Pascal's law. And basically it says, pressure set up in a confined body of fluid acts in all directions with equal pressure. That means if you confine fluid and you press on it, that it acts at right angles to everything, right? See the little arrows? That's how it works. Whatever pressure I apply here is equally applied everywhere at right angles to the whole system. Okay? That's all that says. It says if you confine, basically if you take a water bottle and you squeeze on it until the lid pops off, that's going to happen. That's Pascal's law. This simply says that once it's confined, that a column of fluid is just like pushing on a steel rod. Okay? Now, we're talking fluid, not compressed air. Okay? But hydraulic fluid is compressible. Okay? It's like 0.001% compressible, but we just consider it not. But you can compress a fluid. It's not enough to matter. Okay? So let's talk a little bit about our gauge pressure scale. Gauge pressure, which is typically what we want to talk about, all right, takes into account that all around us is 14.7 psi, our atmosphere. So when it says 0 psi, it's actually not 0 psi, it's actually 14.7. So if we have a psi-G readout, it's showing gauge pressure. All right? Here's psi-G, pounds per square inch gauge. Basically, we just call atmosphere nothing. Okay? Now, that being said, why do we even care, you know? Well, have you thought about airplanes? Because the higher you go in the atmosphere, the lower the air pressure, right? The thinner the air, the lower the air pressure. If you take a psi-G gauge and you have it on the ground and you took it up into an airplane where it wasn't pressurized cabin, it wouldn't read 14.7 anymore. It wouldn't read 0, it would read negative when you got up to atmosphere, or if you carried it to the top of a mountain, right? You understand? You with me? Nod your head. Nod your head. All right. Absolute pressure is referenced against a perfect vacuum, which of course is space, or 0 psi. Okay? So if I was to take a psi A gauge and have it right here, all right, it should say 14.7. Okay? And it always says positive. We don't when we start talking negative, we start talking vacuum, which is expressed in inches of mercury, or Hg. So you know, this is English standard units is what we're going to talk about in here. But so when we talk vacuum, we're talking a whole nother scale and gauge and everything. So here we go. I just told you this one. Vacuum scales, they start at 0 and go down, even though it's a positive number, and it's expressed in inches of mercury. You've probably all seen one of these. It may not be inches of mercury, but like a barometer. What? That tells atmospheric pressure, but that's kind of where it came from. The old barometers actually had mercury in them. Complete vacuum is 29.92 inches of mercury when measuring a complete vacuum. So basically, don't ask me, it was figured out by a scientist in the 1600s. I'm trying to remember his name, but anyway, so they have a 1 inch of mercury in a certain size glass tube, and then they just said, well, when we pull a vacuum, how many inches does it rise? That's all that says. Just like how a thermometer was made when they set up a mercury in a glass tube and said that when the mercury rises so much, that's 1 degree, and we just call it 1 degree. All right, that's what I'm trying to tell you is the instrument came first. All right, just like with temperature, 1 degree, the temperature was designated by a certain rise in mercury in a glass tube. All right. Okay. Now, Boyle's law, compressibility of air. Basically, that says that the absolute pressure of a confined body of gas varies inversely as its volume changes. So that means, basically, if I have this much gas, I have this much air, right? I have a tube with this much air in it, and I take the tube and this is at 14.7, and I squeeze it by half, then the PSI will double. Does that make sense? If the temperature remains constant, because if it gets hot, it's going to expand and the pressure will go up. But at a constant temperature, if I take a volume of confined air and I shrink it by half, the pressure will double, whatever it was to start with, right? So here's an example. If we have 4 cubic feet and it was at 30 psi, and we compressed it to 1 cubic feet, what would be our reading? Actually, they're kind of tricking you because they want you to take into account atmospheric pressure, but for all intents and purposes, really. If this was a PSIG gauge, then that would be correct.
Be 120.
Yeah. It actually, let's see if it's on the next one. Doesn't make any sense. But you have to add in atmospheric pressure.
Right, because it would be 44.7.
It would be 30 PSIG plus 14.7, so it's 44.7 times 4, which will give you 178, and then you subtract the 14.7 back off, which gives you 164. But if it was all PSIG gauge pressure, it would basically be 4 times. Does that make sense? It's just a matter of the scale they're going by. Here's where they're tricking you, because that says
We're using PSI.
they didn't define it, and see how that says PSIG. It's just a trick. I don't know.
PSIG is a closed system.
Yes. Here's how they come up with that. Okay. Charles's law says, it basically says that when you heat up gas, it expands. That's all it says. And we can even see a little right here is Charles's law. Alright, so this is Wisconsin Online, that's where I'm at. We have 50 liters of air shown in this balloon. We move the cloud and the balloon expands. Simple as that. And that basically says that if we heat something up, its molecules move faster. And in the case of air, it gets bigger. If it's confined, then the pressure has to go up. If it's like a stretchy balloon, then the balloon gets bigger. That's all that says. Here it's a confined here, and it says the pressure will rise.
Thus you have a hot air balloon.
Hmm?
Thus you have a hot air balloon.
Hot air balloon. Of course, hot air balloons aren't confined. Hot air balloons work on the principle of hot air is less. But basically, if you have a hot air balloon and when you heat it up and pull the little ripcord to turn the burner on, then somewhere air is blowing back out the edges. Because if it gets big enough, some of the air is going to have to come out of it. Yeah. So you probably didn't notice, but it has to. Which of the following variables remains constant as it pertains to Charles's law?
Volume.
Yeah, let's see. Pressure. Yeah. The temperature of a gas decreases, its volume will
Decrease.
There we go. We also, let's see if I got this. There should be Pascal's law somewhere in here. Where is he at? We're going to skip that one. We're going to go on. We'll come back to it. Okay, Bernoulli's principle basically states that when we restrict fluid in a system, we get a pressure drop right here. So fluid's moving through this pipe, and we squeeze it down right here, and we actually get a slight pressure drop right there. Okay, and you're like, why?
Yeah, counterintuitive.
Well, because it's moving faster, and it kind of speeds up, and it pulls a little bit less vacuum. Now we couldn't do that. I mean, this only applies because, I mean, really it applies in a general. It has to look just like this. It has to be some kind of slope. It has to be narrowed, pinched. Okay. Now, at a certain point, the mass of the fluid gets to the point where it can't easily pass through that opening, and it depends on the thickness of the fluid or viscosity. And then it will actually begin to pull a vacuum and cavitate, which means that there'll be a vacuum pull behind it, and there'll be vacuum bubbles in there, and it'll make a big racket. But this is the general, they use this principle to determine the speed or gallons per minute of a hydraulic or of a fluid system. Like anytime all the water plants around here, they want to know how many gallons per minute are going through their system. And if it's a large volume, the easiest way to do that is they'll put a venturi in it, and they know the relationship between the pressure they have and the pressure they don't have, and that'll tell them the speed of the fluid. It's kind of a basic principle in for measurement sensors. Venturi meters. We will demonstrate this, trust me, because I already got called out on this. And I will demonstrate this to you. I don't have a venturi, but we can pretty much get the same effect using a needle valve to a certain point, and I will demonstrate it. So don't argue with me at this point. You can argue with me after we demonstrate it. So this simply says that we're using Pascal's law when we talk about moving fluid around. I don't know, it's kind of a repeat. But I didn't make the slides. People who made the book made the slides. I added to them somewhat. I put the log splitter in there. Now, what this is saying here is that we can do it like this, or we can save a lot of fluid and metal and do it like this, which is a pipe. All this is a pipe. All right? A pure force with no flow can be transmitted through a pipe of smaller diameter, but if the fluid must move through the pipe diameter must be large enough to keep the flow loss value down. Okay. Depending on how fast you want to move is dependent on the size of your pipe. Most hydraulic systems move slow anyway, and it's not a big deal. But when we get into press actions, large hydraulic presses, then it becomes a big deal.
Isn't that a Ventura there? Where the example
Kinda.
you're constricting there at D?
Yeah, we're going to kind of demonstrate because I don't have a venturi. I wish I did, but and it's hard for me to pull the pressure off. It's kind of a cobbled up mess when I do it, but you can see it a little bit. But there is a pressure loss right here because of that pipe. Longer the pipe, smaller the pipe, we have a pressure loss in the hydraulic system. And you're asking why that is. Well, there's friction going through this pipe. Make sense? Friction through the pipe. So we lose a little oomph to friction. And guess where that friction in turn goes to heat. The heat in turn is carried through the fluid, hopefully all the way back to your cooling system on your reservoir, and you get the heat out, because if you don't get enough of the heat out, it can get hot enough to flash fire. I mean, it's rare that would happen. Most times stuff will melt and fail before then, but you got hydraulic systems make heat, just a given, more so than air systems.
When they're reduced in that manner instead of that venturi the way you showed it, you get more friction because it's not a smooth transition from one pipe to another.
Well, yeah, you can. We get into the deal about elbows and turbulence and stuff later on, but depending how you run your pipes too also takes a little bit into your flow, into your pipe loss over distance. Yeah. So, all this is showing is fluid power has much more flexibility because this is much easier to do with hydraulics than it would be to do with a shaft and gear. Okay? And a screw. There would be a lot of work goes into it. It's much easier to manufacture a hollow tube with a plunger in it than it is to manufacture a big old cam gear system with a swivel anklet with a U-joint on it that would actually have a screw, so there'd be a gear and cam, and then this would go in and out. You can get them, but they cost more than a hydraulic system. All right.
Also have a lot more that wears out on them.
There's a lot more to go wrong. And there's really the only things that are going to go wrong on an actuator is either you're going to break it because you did something wrong or something went bad, or you're going to get a leak. You're going to blow a seal. That's about it. Very rarely do they actually physically wear out because they're always lubricated. So the seals wear out before the metal does. I mean, eventually it will, but pretty much, you know, we've got hydraulic systems that have been in service for 50 years. You can't say the same about a lot of cars and everything, right? I mean, and some of these old farm equipment, farmers have stuff they've been using for 50 years, and they have done diddly to it in 50 years besides maybe change the oil every 5 or 6 years in it, and that'd be about it. And they still work. This just talks about the compressibility of fluid. If this was air, it would have a lot more, and it's pretty easy to demonstrate that fact. Let me see where one's at. Okay. See that? Hopefully that one's not blown. Yeah, we'll just go this other way. Springs back, right? If I hold the air line closed with my thumb, so there is a slight compressibility. If I was to hold this one closed, you get a spring action. That's just all that says. Now I'll set my magic wand down. Oh, there it is. Here we go. I told you some of this was dry, didn't I? Didn't I warn you ahead of time about this class being a little dry? It's fun when we get into the labs.
So what is that last statement there? Why did it say that air is the exception? We compress air all the time.
It says all fluids are slightly compressible, the exception being air, which is highly compressible, is what they meant.
Okay.
Yeah.
We compress air all the time.
That's all they meant by that. So, here we talk about, here's where we get to the area. When we talked about area in our formula. When we're trying to figure out the pressure applied to this, basically figure out the area of a circle. That's part of your formula. Area is, if you're talking about the pressure applied to a round piston, you know the diameter of the piston, you run it through the pi formula, and voila, there's your area. Not a biggie, right? This is simply a simple hydraulic system showing how the pump supplying 800 psi can pick up a load of 9,600 pounds with a 12 square inch piston. It's quite a bit of weight. We've all seen one of these if you've ever been to a mechanic shop and watched them pick up your car and work on it. They're usually about yay big. Usually a single cylinder, and they comes up out of the concrete. Those are those are a little different. We'll get into those are kind of a ram cylinder. And so here we are demonstrating the equivalent of square inches compared to the psi. So notice the weight is the same on each one. As the area gets larger, the psi drops. You see that? Multiplication of force. That's all that says. And we can run the math on that. Hold on a second. Let me pull this back up. I haven't printed these off to give to you, but basically let's look at this one. I know that's kind of hard to read. You can see the area force triangle. So somebody get out their calculator and tell me what area, which is 50 psi times 40, should be 2,000. I hope. Right? 2,000? So, that being said, if we want to maintain 2,000 as our resultant, one of them has to change. So that tells us right there the formula works. If we do the same here, 25 times 80 should equal 2,000, and 15 times 133.4 should equal 2,000. Here we compare it to a lever and a fulcrum, just like I told you earlier. Same principle. Here we see an example of hydraulic leverage where we have 1,000 pounds of force picking up a 2,000 pound weight. This would be a 1,000 pound weight, and because of the surface area of this cylinder being much larger, we can maintain 2,000 pounds. Now, I want you to look right here at the stroke. You see the stroke? That is 4 inches. That's half the stroke. We can't move it as high, but we can pick it up. So that's what we do. We trade off kind of the height of the column of liquid for the ability to pick up bigger load when we talk about multiplication of force in a hydraulic system. Here we talk about static head pressure. Now, here we have this large column of water, 25 feet, or oil, and it's much larger, but at the bottom it has 10 psi. Here we have one that is 1 inch, same height, so it's a 1:24 ratio, and what do we have down here? 10 psi. Now why do we have that? We have that because the same atmosphere that's pressing 14.7 is pressing right here too. That's the reason. Just like if you go scuba diving and you go down to 100 feet in the ocean, and by the way, your little depth gauge on your scuba gear is basically a pressure reading changed into feet, because they figured it up. So if you go 100 feet or the big strip pit and dive down 100 feet, you're still going to have the same force acting on you as if you went to a larger body of water. Otherwise, we'd have a lot of people, scuba divers, with lots of problems at this point. That wasn't true. Let's see where we're at on here. I think we're going to call that one quits right here, turbulent flow. We're going to call it PowerPoint. So just stretch your legs for a second. I'm going to dig out. I want to show you some Wisconsin Online stuff, and then you're free to go. Okay?